So I'm going to use the squeeze theorem to evaluate a limit here that we would otherwise not be able to evaluate using algebraic methods. So if we tried using direct substitution with this limit, we plug 0 in for theta, sine of 0 is 0, and theta is approaching 0. This is an indeterminate form. And I think it might be kind of obvious, but we cannot factor and cancel thetas. You can't just cancel thetas here. That doesn't work with trig functions. Trig identities are not going to help us here because there's no trig identity that tells us what we can do with just the sine of theta. So all those other methods that we've done before are not going to help us. So remember, the squeeze theorem says that essentially we're looking for two functions that are going to squeeze the function in question around the interval, in this case around the interval where theta is close to 0. Now, just to start with here, I'm going to be using this picture to help, and theta is going to be this angle. So I want to be clear that in this video, I'm going to just prove or evaluate that limit. So the limit is as theta approaches 0 from the positive side. We could flip this picture and look at values of theta that are in the fourth quadrant and look at what happens when theta approaches 0 from the negative side. That would be a really similar process, but I'm just going to focus on this one, and then you can just trust me that it works in the fourth quadrant also, and so we're going to get the same thing. So this is going to be a process that would not be immediately obvious to somebody that's trying to evaluate this. This is not a process that I'm going to expect you to reproduce on your own. But the idea here is I'm going to create that inequality we need for the squeeze theorem by using some areas in this picture. All right, so there's three areas that I'm going to look at, and I'm going to start with what I'm going to call in this problem the small triangle. So the small triangle I have highlighted here in blue, and I want to find the area of that small triangle. So area of the small triangle. So I'm going to use some variables here. I'm just going to call this distance right here. Make sure we know what we're talking about here. That distance I'm going to call x. This distance I'm going to call y. And using a little bit of trigonometry here in this small triangle, the sine of theta is going to be, sine is opposite over hypotenuse. So opposite is y. And then this is a unit circle that I have in red here. So this part right here is going to be 1. So sine of theta is y over 1. And cosine of theta is going to be x over 1. So the area of the small triangle is going to be base times height divided by 2, which for this particular one with the equations that I just wrote down is going to be, let's see, that should be x over 1. So x is going to be cosine of theta times y, which is sine of theta, all over 2. All right, so that's our first area that we're going to use, and that's the area of the small triangle. Another one that I'm going to use, I'm going to call the big triangle, is this triangle that I have highlighted here in purple. And to find the area of that triangle, we're going to do the same thing, base times height divided by 2. In this case, the base is 1. So, I erased part of my A here. Pardon the color difference. So the area of the big triangle is going to be base, which is 1, times the height, which we're going to need a little trigonometry here. For this, I'm going to use the tangent function. So the tangent of theta is going to be opposite. I'm going to call that h for now. So it's going to be the opposite over adjacent. And so the height is going to be tangent of theta. So it's 1 times the height divided by 2, which is going to be tangent of theta divided by 2. All right, the third area I'm going to use is going to be a sector. So if you remember, a sector is a part of a circle. It's essentially like a pizza slice of a circle. So this that I have highlighted in kind of magenta here, that's a sector. And to find the area of a sector, you might remember from geometry class taking the central angle of the sector divided by 360 and then multiplying by the area of the entire circle. Well, you divide it by 360 because that's the total number of degrees in a full circle. We're measuring in radians here, though. So instead of doing the central angle divided by 360, I'm going to do the central angle divided by the total number of radians in a full rotation, which is 2 pi. Okay, so this is the fraction of a circle that we're dealing with here. And then multiply that by the area of the unit circle, which is pi times the radius squared. And simplifying that, pi's are going to cancel each other out here, and we get theta over 2, okay, which is a pretty simple expression here. And so the area of that sector is just going to be theta over 2. Now, looking at these three areas, I claim that no matter what angle theta is in this picture, the small triangle is always going to have an area that's smaller than the sector, and the sector is always going to have an area that's smaller than the big triangle. So we get an inequality that is going to look like this. So I'm going to start with just the areas here. So the area of the small triangle is going to be smaller than the area of the sector, and that's always going to be smaller than the area of the big triangle. Now, if theta were actually 0, and remember with a squeeze theorem, we don't really care about what happens at 0. If theta were actually 0, these would be less than or equal to, because all of these areas would be 0 at theta equals 0. I'm going to leave them just strictly less than. Squeeze theorem works either way, so it could be less than or equal to. Either one would work. So just filling in the expressions that we have here for each of those areas, area of the small is going to be cosine of theta times sine of theta divided by 2. Area of the sector is going to be theta divided by 2. And the area of the big triangle is going to be tangent of theta divided by 2. Okay, so we have this inequality here. Now, you might be thinking that inequality doesn't really seem to help when we're trying to evaluate this limit right here. So what we need in the middle for the squeeze theorem to work is we need this expression. So to get that expression, what I'm going to do is just a little bit of algebraic manipulation. So I'm going to take what I have here, and let me just clear some space for myself. I'm going to take what I have here and do a little manipulating. The first obvious thing is we can get rid of all these 2's. We don't need those. The second thing I'm going to do is I'm going to get theta in the denominator. So I want theta in the denominator here because theta should be in the denominator in that middle part. So to get theta in the denominator, I'm going to take the reciprocal of each one. All right, so I'm going to start by just writing that. And if I reciprocate each of these, 1 over tangent, let's think of tangent as sine of theta over cosine of theta. So when we take the reciprocal, it's going to be cosine of theta over sine of theta. By taking the reciprocal, let's think about what's going to happen. So if we take a bigger number and we take the reciprocal of it, we're doing 1 divided by that bigger number, we're going to get a smaller number. So when we take reciprocals with an inequality, those inequalities are actually going to flip. So we should get an inequality now that looks like this. All right, so we're a little bit closer. What we want in the middle here is sine of theta over theta, because we want this function there. So all I'm going to do is I'm going to multiply by a sine of theta. Now remember, with inequalities, if we were to multiply by a negative value, our inequalities would flip again. But remember, we're in the first quadrant. Theta is a first quadrant angle, so the sine of theta is going to be positive. So when I multiply by the sine of theta, I'm going to do this informally like this first. When I multiply by the sine of theta, I'm multiplying by a positive number. My inequality is going to stay the same. Okay, so in the left part here, multiplying by the sine of theta is just going to cancel that. In the middle, we're going to get sine of theta on top. And in this one, we're going to get the sines cancel and we just get cosine of theta. So the inequality we have left now is 1 over cosine of theta is greater than sine of theta over theta, and that's greater than cosine of theta. Now, I want to remind you again, we're dealing with theta values that are in the first quadrant, so between 0 and pi over 2. And this range of theta values is what we need if we're trying to evaluate this limit as theta approaches 0 from the right. Okay, so now the squeeze theorem says that if the limit as this approaches 0 and the limit as this approaches 0 are the same thing, then the limit of our middle function also has to approach that same thing. So let's evaluate those. We have the limit as theta approaches 0 from the right of 1 over cosine of theta. We can use direct substitution here. We plug 0 in for theta. Cosine of 0 is 1, and 1 over 1 is 1. Then over here we have the limit as theta approaches 0 from the right of cosine of theta. So we're doing this one now. We can use direct substitution again. So cosine of 0 is 1. So these two match up, which is great. So that means that as theta gets closer and closer and closer and closer to 0, this expression gets really close to 1, this expression gets really close to 1, and this one is squeezed in between them. So as both of those expressions get closer to 1, this one has to get closer to 1 because it's between the other two. So that means then that this limit right here is equal to 1. Now I mentioned earlier, what we're doing here is finding this limit as theta approaches 0 from the right side, so a first quadrant angle. We could go through the same process with an angle that's in the fourth quadrant as theta approaches 0 from the left. And we would have a few things that are a little bit different. Remember, sine is negative in the fourth quadrant, so we're going to have to deal with that. But for the most part, it's going to look really similar, and we're going to end up with 1 for that limit also. So according to the squeeze theorem, this limit is going to be 1.